All right, Henrik, thank you for making the trip here. I very much appreciate it. Your work is fascinating, and I'm sure there's a lot of stuff, a lot of different rabbit holes we're going to go down during this podcast. But to start this thing off, how did you initially make this discovery that essentially, like, the high-level view is you're positing that where the Earth sits in the Milky Way Galaxy is directly responsible for geological climate change on Earth?
That's true, but that came later.
Okay.
So it actually, I mean, the initial thing has to do with solar activity.
Okay.
There were some ideas that if you have change in solar activity, then there were some changes in climate. It's an old thing, and it's something people have been speculating.
What? The sun affects the climate? Who would have thought?
Yeah, but I mean, you will be surprised how little effect it is believed to have in the what you call the International Panel on Climate. But anyhow, there was these ideas that when you have a change in solar activity, there seems to be changes in climate if you go back in time. So it's an old idea. And I was at the Meteorological Institute at that time, and I was looking for something interesting to do. And when I heard about this agreement between solar activity, I thought that if it's going to work, the most effective way would be if solar activity somehow changes the Earth's cloud cover. So that was the idea. I mean, you probably know that clouds, they have a big impact on the temperature on Earth. So
because they reflect sunlight?
They reflect sunlight. So they do two things. They both reflect and they also keep the heat. But the reflection is what, wins. It has the largest contribution.
So what made you think that the solar activity had to directly affect cloud activity or cloud formation?
The idea was immediately that it had to be with cosmic rays. So cosmic rays, what are they? They are particles that comes from our galaxy, our Milky Way. They're very energetic.
Bless you.
They're very energetic particles, and they shower the Earth. And the idea was that I remember when I was in high school, I worked with what called a cloud chamber. That was what we saw just before, a cloud chamber where you have particles where you can see the streaks of the particles. So just like you have an airplane, you can see in the sky, you can actually see when the charged particles go through in a cloud chamber. So what happens is that you have a supersaturation, typically some alcohol, and then each little charge, it condenses this liquid, and you see these small droplets. So that's why you see these streaks.
Okay.
This is what you see here.
Okay. Oh, this is the cloud chamber.
So this is a cloud chamber, and you can see these long streaks, and these are what we call these are cosmic rays that are entering through a very thin layer where the cloud chamber is active.
Oh, wow.
So, and the very long straight streaks, these are called muons. These are actually produced in 11 kilometers or 13 kilometers or 20 kilometers, and then they move down through the atmosphere. So you have a collision just like with billiard all the way down through the atmosphere. I mean, we can actually...
Wow.
You can see it if you look at if you take the one before number 5, yeah. So what you see here is from 25 kilometers and down through the atmosphere. You see one particle is coming in with a very high energy, and then you are producing a shower of secondary particles.
Wow, it's like a shotgun blast.
It is.
And these are a cosmic ray.
Yeah, it's called a ray because when they first discovered them, they didn't know really what they were, but they are particles.
So it's a sun particle.
It's not from the sun, it's from our galaxy.
From the galaxy. Okay.
So it's called galactic cosmic rays.
Okay.
So, And the thing is that if we go outside, when solar activity is changing, it modulates how many of these particles enters into the atmosphere.
Okay.
So solar activity can sort of regulate the number of particles.
So like solar wind, if we have lots of solar wind around like the Van Allen radiation belts, it can deflect lots of these cosmic rays away from the Earth.
The solar wind, yes, exactly. It sort of screens against these cosmic rays, so they're just sort of scattered out into space. And these changes in cosmic rays are some of the largest that you have with respect to changes in solar activity. So you can have maybe 10, 15, 20% changes in cosmic rays.
And what is so unique about these particles that we call cosmic rays?
These are mainly protons, meaning that they are the simplest element that we have. So there's hydrogen, the core nucleus of the hydrogen.
Okay.
And the origin of these particles, we can talk about that, is actually when big stars explode.
Oh.
So these are what we call supernova explosions. And when you have a supernova, you have this expansion of a shock front. And then these charged particles can get accelerated to enormous energies. So you can say that this works as a cosmic accelerator that makes these particles, they give them enormous energy.
Wow, and it just blasts them outwards.
Yes.
Through the rest of the Milky Way.
Yes.
And it hits.
So it sort of fills the whole part of our Milky Way, and where we have the solar system, the particles, they enter, and solar activity can then modulate it.
Okay, so these cosmic rays, how do they make clouds?
That is then the thing. In order to look how...
And you didn't know they made clouds. You had to figure this out.
I had to figure it out, yes.
Right, okay.
So if we look at number 14, I think, if you look at... Yeah.
Okay.
So if you look at the left-hand side, you can see you have free charges which are made by cosmic rays, and that stabilizes very small molecular clusters, and they're only about 1 to 2 nanometers. A nanometer is 10 to the minus 9 meters. It's so small you cannot see it. So it's only, a few molecules that stick together, but because of the charge, they are stable, so they don't evaporate again.
Okay.
And the idea is that if you produce more of these small aerosols, then as a function of time, they grow because they take up more gas, and you can have they collide, so they sort of, stick together. And then at some point, they are, about 50 nanometer. And then you can call them cloud condensation nuclei, because in order to produce a cloud, it consists of cloud droplets. You have to have a surface on which water vapor can condense.
Okay. And those are the cloud droplets.
And then become cloud droplets, and if you have sufficient of them, you have a cloud.
Okay.
So the idea is that if you now have more cosmic rays coming in, then you are producing more of these cloud condensation nuclei. If you press... just press one time down... yes. So what you see up here is an indication that if you change the number of cloud droplets, you are changing clouds. What you see up here is a region from a satellite image where you have low clouds, and then you can see that there are these stripes, and these are ship tracks. So what happens is that the ship is pumping out, particles from the engine.
Yeah. And
then that goes into the clouds, and you can see it changes the clouds.
Wow. Like cargo ships in the ocean.
Yes, so they change the cloud. So it's just like airplane. You see it, but here it's in low cloud. So what it shows is that if you can see it here, if you change the number of cloud condensation nuclei, you change cloud properties.
Whoa. So what are the differences between this left and right? By the way, for people that are just listening, I highly recommend you watch this on video, either on YouTube or Spotify, because this is going to be a highly visual episode. So what are the differences between the left and the right here?
These are just different cloud scenes where ships have been sailing. So, and in the one in the right, you can actually see that it is really clouds that have been changed. Mm-hmm. So the idea is that if the cosmic rays can do this systematically all over the Earth, because they are omnipresent cosmic rays, then it would be a very effective way of regulating the Earth's climate.
Wow. And you were the first one to posit this.
I was the one that said that there is this connection and that seems to be real.
And what has been the feedback from the scientific community on this specific connection that you've made here?
I mean, I did it in 1996. There was a conference in Birmingham where it was presented the first time, and a newspaper, a Danish newspaper, put it out. And I mean, before that, nobody cared what I did. After that, it was completely crazy what happened, and we got an enormous reaction and very aggressive reactions. I remember coming back from the conference, and there was a headline saying, strong UN critique of Danish researchers. That was the International Panel on Climate, which is under the UN, saying that what we had done was naive and irresponsible.
Naive and irresponsible. Did they disprove the connection that you made between?
No. Nobody has disproven anything.
Okay.
So, but
nobody has said that the connection that you've drawn here with your evidence is everyone said that it's legit. No one's proven that it's.
Let me put it this way: when we started, everybody was saying that we don't know any known mechanism that can do this, so it cannot be true. I think now the next step is that they're saying, okay, maybe there is an effect, but it's not important. And the final thing is that they say that this is what we all said all along.
Now, when you first came out with this, did you publish it to like a scientific? I don't know how that whole process works. When you're a scientist, you put it published and all that.
Everything I've been doing is going through the normal way of doing things, which is to find the results, write them up, and publish them in good journals. So it's what you call peer reviewed. Peer
reviewed, yeah.
So there's no guarantee that things are correct, of course, but someone has seen it through and says that, okay, let's our colleagues consider what you're doing.
Right. Okay. So you made this connection with the cosmic rays being specifically associated with cloud formation.
Yes.
Now, how do you extrapolate that into a correlation of the cosmic rays being primarily responsible for the change in the climate on Earth?
Well, the idea is that if you change the clouds, you change the amount of energy that goes into the Earth's system. So if you have a systematic changes in clouds, So let
me ask you this. Sorry to interrupt, but is it accepted with the mainstream that clouds are primarily responsible for the climate?
Well, it is mainstream that clouds are important.
Important.
Yes, and another thing that is extremely, everybody knows that clouds are the the most difficult subject in all climate modeling, because it's so difficult to model cloud processes.
Right.
So if you have a systematic change in clouds, and this is well known, I mean, if you look at marine stratus clouds, which are the low ones that you always see when you fly over the oceans, these endless scenes, if you change that just by 1 or 2%, it is similar, to all the greenhouse gases. The change in greenhouse gases, so it's 1 or 2 watts per square meter. So it is really important.
The low clouds.
Yes, marine clouds. Yes.
Interesting.
So I mean, if you show slide 13, you can see the figure that actually started the whole thing. So what you see here is since 1983 until 2005, and you can see the red curve is the change in cosmic rays over the until 2006.
Wow.
And the reason that you have this change is because of solar activity. So it's the 11-year cycle that you see. So solar activity is modulating the amount of cosmic rays, and the blue curve, that is actually low clouds over this period. So you see there is a beautiful correlation, but it doesn't mean that we understand why it's there.
Wow.
So
that is amazing.
That's how it started.
So for people that can't see this graph, from 1985 to 2005, the correlation between cosmic ray activity and low cloud coverage is spot on. Like it tracks perfectly throughout that whole time. So let me ask you this though: how do you track the cosmic ray activity going back that far?
I think since the beginning of the 1950s, you have been measuring systematically cosmic rays with something called neutron monitors.
Wow!
So
we've had this since the 50s.
Yes, in the 50s. Yes, it was an American actually that started this part. Neutron monitors are operating, and they're measuring all the time. So you can see changes in cosmic rays.
We make predictions every single day about pop culture, politics, sports, even the economy, and major news headlines. Kalshi, which is America's #1 predictions market platform, lets you trade on these predictions on a live market. Here's one that fits this show. Will the U.S. confirm that aliens exist before January 20th, 2029? Right now, that's trading at a 22% probability, meaning a $100 trade would pay out approximately $400 if the U.S. confirms it. On Kalshi, you're trading against peers in a live market, meaning no house. And as the probability changes, you can buy in and out of your position. Download the Kalshi app and use the code DannyJones to get $10 when you trade $10. It's Kalshi. Kalshi. Trade on everything. 18+. Restrictions and eligibility requirements apply. Event contract trading involves risk and may not be suitable for all investors. Prices, values, and available markets may differ from those mentioned. For more information, see kalshi.com/regulatory. Past 1950, we can't go any earlier than that as far as measuring cosmic rays?
We can. But it has to do with, you have to do it indirectly. So we call it proxies. Mm-hmm. So when cosmic rays comes into the atmosphere, they are producing new isotopes. That is the new elements. Carbon-14. You've heard about carbon-14?
Right.
And carbon-14 is produced by cosmic rays. And so then you can imagine that you have this carbon is slightly heavier than carbon-12. Mm-hmm. So it goes into, it sticks to oxygen. So you have CO2 with carbon-14, and it goes into leaves and goes into a tree. And then in the tree rings, you can measure the amount of carbon-14 relative to carbon-12 in all the tree rings.
Oh, wow.
And if you measure that, you can then say something about how solar activity has changed back in time. So it's something you have to take into account also when you're doing, archaeological studies. You have to take into account that solar activity has been changing. Otherwise, you will get completely different ages.
I've seen models of the climate, the Earth's climate, going back we've pulled them up on this podcast, going back 50 million years. How do they accurately figure out what the climate was 50 million years ago?
There are indirect methods, and one is to use what we call oxygen 18. It's again isotopes.
But this is the cores, the ice cores, and all that.
Ice cores only go back 800,000 years.
Oh, really? Okay.
And they're best 100,000 years back, or a little more. But if you want to go even further back, one thing is that you can take some. It's interesting because you take some animals that lived, some shells,
fossils.
Yeah, fossil shells. So in the shell of the fossil, you measure how much oxygen 18 there is relative to oxygen 16, and that says something. It says something about how hot the water was when the shell was formed. So you can go in different layers of the Earth and find these fossils and measure, and that gives you a proxy of the temperature as you go back. And I have things I can show you.
Oh wow, that's amazing.
Yeah,
I've seen different things. I've had geologists show me different layers of the sediment where there's this black matte layer that correlates to 12,500 years ago or whatever during this Younger Dryas event.
Oh yeah, yes.
And lots of people believe that or speculate that there could have been this crazy asteroid impact or comet impacts throughout the Earth, that when we passed through a specific cycle or when the Earth passed through a specific zone of the universe or whatever, there was high asteroid or comet activity that could have been responsible for that, like a mass extinction event or something.
Yes, that's. I heard that too.
And then allegedly everything was flash frozen, and then everything was got really hot, and then there was a flash freezing event where the sky blacked out and everything got super cold.
Yeah. It makes a big change.
What do you make of that theory?
I think it's interesting, and you try to find the evidence in the ground, so that's fine.
So, what's next? As far as your discovery, in the process of you making this discovery and presenting it to the public, you're now showing people that, and you've got papers that prove that this specific activity of cosmic rays correlates to climate going back to at least 1850 or 1950.
It correlates, yes, and the big problem. These are correlations. That's what was the start of the whole thing. So you have to. Because there's a correlation, and this was something that people were telling me all the time, that just because you have a correlation, that might not be causation. So the idea has been to try to figure out how to prove or investigate what the mechanism could be. Because you have to, go further into the problem. And very early, I realized that we had to do some experimental work. And around 2004, and maybe even earlier, I built a laboratory where we could make this type of experiments. If you look at, I think it's slide, it's a 16. Can you see that? You can see here, these are all the places that we have been doing experiments.
CERN, the DTU National, this is the Danish National Space Institute?
Yes. And
at the Astrid Accelerator? I haven't heard of that one.
No, it's in Aarhus. It's in Denmark.
Oh, okay. Okay, yeah.
And then you have CERN in Geneva.
CERN, yep.
And then at some point we went 1.1 kilometer underground in a mine because we wanted to avoid cosmic rays. And you have to go that far down in order to get the cosmic ray intensity down by more than 1 million.
Really?
Yes. So they are very, very penetrating. I mean, as we sit here...
How deep again?
1.1 kilometer.
Wow. As we sit here, we're getting pelted.
Pelted, and they go right through us, and there's nothing, spectacular as such, because this is happening ever since, for the last 3 to 4 billion years for all life. So it's part of our environment.
Okay. So what was going on at CERN?
At CERN, we did some pilot experiments. There was a project called the CLOUD project that was built at some point. I was part of the CLOUD project in the early stages, but then I switched to our own. We did experiments where we actually showed that, yes, there is a microphysical mechanism if we increase the ionization in a large chamber. We can see that we are building small aerosols. So we can measure that, and we could sort of document it. I think if you go to...
So that's the reason for going so far underground, is to create your own, spray your own cosmic rays. At your experiment, you have to eliminate all the cosmic rays coming out.
That was the one in Bulby, yes.
Right.
But the one in the DTU, the National Space Institute, there we have some gamma sources outside the chamber, and then we have some, we call them, we have some LED, walls that we can move.
Right.
And then we can increase the ionization in the chamber, and we can turn it down. If you go to the next slide, I think there you can see one example of such an experiment. You have cosmic rays, or this is actually ionization, that increases along the bottom axis. And then you can see as we increase the ionization, we actually produce more of these particles. So it's just an indication that there is a microphysical mechanism that links the two.
So Earth's climate goes up and down,
yes,
and, constantly throughout history.
Yes.
And we've seen this just from the graphs that we've already seen before that just show the climate. I mean, we have like the medieval warm period. We have, it seems like right now, just based on the last couple million years that we've tracked, that right now it's cooler than it's been on average over millions of years, over the last at least 5 million years, right?
Yes, it is much cooler. If you go back 50 million years, Earth might have been 10 degrees warmer than now. So you had, palm trees in Antarctica at that time, and baobab trees and so on. I mean, so it really is something that here we go 3 million years back. So. But yeah, you can see there has been a steady cooling over the last few million years.
Yeah, so this blue one is... What is the blue one, Roger?
It's more ice.
More ice.
More colder. When it goes down, there's more
atmospheric CO. So that's the question. Is there a correlation between the temperature and the atmospheric CO2?
In the ice ages, yes.
In the ice ages?
Yes. You see a very clear correlation. The thing is that it's probably CO2 that is reacting to the temperature and not vice versa.
Oh.
So you can actually see if you make, if you look very closely at the data, you can see that the temperature changes first and then the CO2 changes. This is something, it's commonly known.
So in the ice ages, it was very low CO2?
Yes, and yes. It was so low that, it was a problem for plants at that time. That's also why instead of C3 plants, you developed the C4 plants. They are much better at taking up CO2 than ordinary plants. If you go too low with CO2, all life dies.
Interesting. Right. Yeah, no, I knew that. But so that what you're saying, which is counterintuitive to mainstream knowledge, is that, or mainstream, whatever the narrative is that the CO2 reacts to the climate. So if it's a really hot climate, the CO2 will go up.
Yes.
Got it. So why do people say it's the opposite?
It's because here, in the modern period, we are burning fossil fuels. Mm-hmm. So we are putting in more CO2, and CO2 is a greenhouse gas. So so by putting in more artificially, we can, of course, raise the temperature a little bit because of that.
Oh, okay. Okay, so you're saying that the man-made carbon dioxide that does go into the atmosphere every day, that does have a little bit of an effect on the overall temperature, but it pales in comparison to what these cosmic rays forming clouds can do.
Yeah, on the longer time scales, as I can show, is remarkable correlations on the long time scales, yes. Mm-hmm. But also, if you look at you talked about the Little Ice Age.
Right.
That is a period where you had very few sunspots, so very little solar activity. So therefore, there was much more cosmic rays coming in during the Little Ice Age, and that is a beautiful correlation.
So that's an interesting thing that you said there. That's kind of hard to try. It's kind of counterintuitive. It doesn't really, until you really understand it, right? You're saying that the low amount of solar activity equals more cosmic radiation.
Exactly, because the sun forgets to throw away the cosmic rays, right?
Right.
So when the sun is at low activity, the cosmic rays don't get so much resistance in going in.
And more solar wind, more sun activity, the least amount of cosmic rays.
Yeah, and warmer climate.
Yeah. The more cosmic rays we get, the more clouds we get, and the cooler the climate.
Yes. And it's also interesting, when you had the Little Ice Age, you had, when you had bad weather and so on, you at that time they believed it was because of witchcraft. And it's amazing because so many women were burned at the stake because of if you had a bad storm. They had to find the culprit, and that was, witchcraft. Mm. So at that time, many thousands of women and men also were burned at the stakes because of bad weather. There are some storms. There's a famous thing with a Danish...
Listen a little closer to you.
Yeah, there was a Danish princess that was going to be married to an English king, and they were trying to sail from Denmark to England, and they were hit by a bad storm. And because of that, the king thought that it was witchcraft, so they actually... executed a large number of people because of that storm.
Jesus. Yeah, the things that human beings have done in response to weather or to try to make the weather change going back is just, the Mayans would sacrifice people to appease the rain gods, for crops and stuff like that. Starting a business can be a big deal. And what really shocked me was how simple Shopify made the whole process. We use Shopify for our merch store, and we were able to recently revamp all of our products. And from day one, it felt like the tools were simple and easy. Instead of feeling like I was learning a new profession, the design part was way easier than I expected. Shopify's templates and AI tools helped us get the storefront looking clean, professional, and real without needing to touch any code. Then once people started buying, Shopify's checkout made a huge difference. Customers move through it really fast, and returning buyers can check out in a single click. And that's when you hear that little... because the process just works. And if you ever hit a wall, Shopify has a sidekick that's built in. It's their AI assistant, and it helps you troubleshoot, build, and keep moving without wasting hours stuck on one problem. All you need is the idea, and Shopify handles the rest. Start your free trial at shopify.com/DannyJones today. Again, you can start your free trial at shopify.com/DannyJones. It's spelled shopify.com/DannyJones. So you say that the magnetic field of the sun has more than doubled in the last 100 years. Is that right?
There has been an increase in solar activity over the last 100 years, yes. I can't remember. There was a paper at some point where they said that the sun's magnetic field has more than doubled over the last 100 years.
Do we know why?
No, but it has to do with solar activity, and solar activity is not something that is well understood. Mm-hmm. So, for instance, when we say that there might be a solar minimum, that is a very low solar activity in the future, it's very uncertain because we cannot predict these things very good.
Mm-hmm.
But we know that there has been a large number of what we call minima in solar activity. I mean, 6 or 7 times during the last 10,000 years.
Mm-hmm.
And each time you have a very cold climate. I mean, I can show you a very beautiful. If you look at number 10 of mine, let's see. No, was that number 10? Oh, sorry. It's number 8.
Number 8.
Yeah. So what you see here is the last 12,000 years. If you look at the bottom figure, and the black curve is actually an expression of climate, and it's an indirect way of getting the climate. It has to do with icebergs that moves over the North Atlantic,
Mm-hmm.
and when they move over the North Atlantic, when they melt, they have a lot of small stones in the ice that then fall down on the bottom. And then you can drill up these ice cores, and then you can see how many small stones there are as a function of time. And that says something about how many icebergs have moved over the North Atlantic.
Oh, wow.
And that's the black curve. And the blue curve is changes in cosmic rays over that period.
Oh, wow. That's incredible. So, and explain what you are saying about when it comes to the Milky Way Galaxy and where our solar system is currently in the Milky Way Galaxy is constantly changing, right? And is it our solar system goes around the whole Milky Way Galaxy, does one rotation in what, like 100 and something, 200 million years?
Yeah, 230 million years.
230 million years, we make a full rotation around the Milky Way Galaxy.
Yes.
That's crazy. And each rotation, we go in and out of the arms.
Yes. And the arms are not sort of material arms. It's actually a wave phenomena on top of all the stars that are moving around. And the reason that they look more bright is because that's where you make a disturbance, and that's where you have the star formation. And that's also where the young stars that are large stars are, and they're much more bright. So that's why you see the spiral arms as bright arms. Mm-hmm. And we are moving in and out of these regions. And when you have more star formations, that's also the places where the large star explodes. And the large star that explodes are the ones that produce the cosmic rays. So when you are in a spiral arm, you get much more cosmic rays. And the changes are, maybe 300% change in the amount of cosmic rays.
Wow.
And then opposite, when you go between spiral arms, then...
Can you show, do you have like an image of this that we can see to give a better understanding of it?
If you look at number 31.
31. So these bright spirals that we see, this is where you're saying a lot of the new stars are born and dying?
That is where the new stars are born. A lot of stars is born, and new stars are dying. I should say that I work closely with a guy called Nir Shavib. He's a professor in Israel. And I worked with him for many years. He's the one that took up this idea. So he's the one that he made this idea that when we go through spiral arms, it should be important for climate on Earth.
Really?
And each time we are in a spiral arm, there seems to be a glaciation on the Earth. So it's a cold climate. And I can show you...
When we're in the spiral arm, it becomes very cold.
Yes, because you have more cosmic rays, and more cosmic rays mean more clouds, and clouds are cooling.
Right. Wow. Okay, so what is it about... Why are more stars being born and also exploding in these spiral arms?
It's simply because in the Milky Way Galaxy, it's like a disk, and in the disk there's a lot of gas in the form of hydrogen, and hydrogen is the basic element in stars. So what is happening is that you have sort of a disturbance along the spiral arms of the gas, and that makes the gas sort of collapse, and it becomes more and more dense, and then at the end it ignites the stars.
Whoa!
And when you ignite the stars, you are actually producing a whole range of different size stars, and some of them will be the heavy ones that, because they are heavy, they burn very strongly, and they don't live very long. So you only live maybe between 3 and 15 million years, and that's a short time compared to the rotation. So the very, very bright stars, they are typically have a short lifetime in close to the spiral arms. And that's why you get more cosmic rays in the spiral arms.
Wow. That's so hard to comprehend, just the scale you're talking about. Like, you're able to explain what's happening, chemically within the entire Milky Way galaxy. It's so crazy. And so where is on this giant diagram of the Milky Way galaxy, where is our solar system roughly?
Well, you can see there's the sun location with the star in the bottom. So we are about 1 or 2/3 outside. And we are actually moving around the galaxy, the center of the galaxy, within about these 240 million years. And then we go in and out of the spiral arms.
So let me ask you, this might be a dumb question. This might not be the right person to ask, but are we moving away from the center of the Milky Way galaxy consistently, or is it staying about the same?
It's staying about the same. I mean, it's not a perfect circle, of course.
Right.
But because there are some disturbances, but it is more or less, for all practical, we can call it a circle around the galactic center.
Is it?
The sun is what we call a disk star. And all the disk stars are moving around the galaxy.
Why is it a disk star?
It means that it's because when you have star formation, many times they are born in a cluster. So you have many stars that are bound together by gravity. Do you want to see this process?
Oh yeah, of course.
Okay, then go to number 57. It's simulation. Okay. So you can see how.
Perfect. So you're talking about like binary star systems?
So here you have a gas cloud, and it has been disturbed, and now it will start collapsing, and you will have star formation. And you will produce a large number of stars. You can see a lot of... so this small white is actually stars that are igniting.
Oh, wow.
So,
what is that stuff that's like popping out of them?
That is gas that is being accelerated and thrown out. And I even think in this there is a supernova going off. You can see that they throw out some stuff.
Wow.
So at this time, these stars are all from the same cloud. So you can say all these stars are siblings in the sense that...
in the same cloud.
Yes. And then what happens, at some point, I think it ends, you can sort of zoom out a little bit, and you can see that you have what we call an open cluster. This is an open cluster of clouds.
So what we're looking at right now
is star formation.
This is star formation, right?
Yeah.
But like on the, can you give me like a relative scale?
Yeah, it's probably 150,000 years or something like that.
This is about 150,000 years. And how big are each of these stars that we're looking at compared to like our sun?
They are probably, many of them are smaller and some of them are bigger. They form after, it's always formed, there you had a supernova going off actually. But you see, it's like a This is what we call an open stellar cluster. And the reason I'm showing that, it's because I have been using open stellar clusters to go even further into this problem on the long time scales.
Superstellar clusters.
Open stellar clusters. Open. Yeah, because you remember we started asking the question why it's a disk star.
Exactly. Yeah.
So here you have stars which are part of a cluster. So what is happening is that they sort of move in between, and there might be some disturbances, and then the stars they sort of fall off. So the gravity can no longer keep a star bound, and when it falls off, it becomes a disk star. So our sun probably also was born in this way.
And then it eventually just like drifts out.
And it eventually drifts out, yes.
So there could be no life in one of these clusters. It's too hot, too many stars.
Well, it's very young at this point, right? So it hasn't had time to evolve. But I mean, there probably will be planets and so on around some of these stars, yes.
Inside this cluster?
Yes, there will be start the formation. I mean, now we know that nearly all stars have planetary formation.
Wow. So, that is bananas.
So, if you go to number 34, what I'm showing you here is the number of. If you in the middle there, in the middle of this circle, that's where the solar system is, and after these dots is an open stellar cluster. So these are open stellar clusters. That is a group of stars, and the color, it says something about how old the cluster is.
Oh.
And you can see most of them are about 100 million years.
So the dark purple at the bottom is how old?
100 million years.
And what's the red?
And red is 1 billion years.
1 billion.
And you see there's very few of the old ones. And that's
not many old ones.
No, and that's because they have evaporated. So all the stars have been falling off, so they no longer exist.
So they exploded?
No, they fall off, so they're no longer a cluster. So it drops stars, and each time you have fewer and fewer, and in the end, there's nothing left. So they're all becoming disk stars.
Ah, okay, I see now.
So, and in this plot here, there is information about star formation over the last, for instance, 500 million years.
Mm-hmm.
So if you move to the next slide, you will see a reconstruction of the number of supernovas over the last 500 million years.
This is 500 million years right here.
This is 500 million years, and you can see that the changes in supernovas or the supernova activity is almost a factor of 3. So for 300 million years ago, there was a lot of cosmic ray or a lot of supernovas going off.
And you're measuring this directly by the proxy of the cosmic.
This is measured by these open stellar clusters that I use the information in them to say how many stars were born at a certain time. When I know how many stars have been born, I know what fraction have been large stars, and then I know how many will explode and produce cosmic rays.
Okay.
So it's an indirect way because we have no way of doing it.
Got it.
But I mean, it looks very.
So you can use basically Earth's climate history to reverse engineer this stuff right here.
That's a good question. What you have here is only astrophysics.
Right.
There's nothing. The top bar you can actually see when there's glaciations and when it's cold. So you can see over the last. In the first part, you have the first 30 million years. You have a large glaciation.
Lots of supernovas.
Lots of supernovas. And if you go 300 million years back, you can see there's glaciations, severe glaciations again. And there seems to be a very nice correlation with this figure as you go back in time.
Wow.
But let me take it even further. If you take the next slide, what you have here is only 200 million years. And what I've done here is I've used a proxy for temperatures going back in time. Remember we talked about these shells. I think they're called brachiopods.
Fossils, like fossils?
Yeah, these are fossils. And then you measure the amount of oxygen 18 relative to oxygen 16.
And you can figure out the water temperature, right?
And that gets you the water temperature. And this is what you see with all these dots. Each of these dots is a fossil.
Okay.
And you can see the red curve is the change in supernovas. And you can see there's a beautiful correlation between the two.
Oh, interesting.
And when there's many supernovas, you can see that it's actually quite cold on Earth. And when you go back, I know, for instance, 50 million years, it was much, much warmer.
Wow.
And also, I think it's quite interesting because if you look at just the last 30 or 40 million years, you can see there's a sort of a minimum at around 30 million years. That minimum is also shown in the data for the temperature. So there's this. I mean, it's actually a quite beautiful correlation even on these timescales.
Have you noticed any sort of pattern in this activity? Like every, 10 million, 20 million, 50 million years, is there, I mean, obviously there must be some sort of a relative period of time in between each one of those arms in the Milky Way Galaxy, right?
Yes. And this is, I mean, if you look at the beginning, that's because we just passed the spiral arm. If you then go back and you see that there's a minimum around 140 million years ago, this is another spiral arm that we go through. So you can actually see the spiral arms in the data.
Wow.
And when we go through a spiral arm, it's actually colder. When we are in between the spiral arms, you can see
it's hot like a desert.
Yeah, it's really, really hot. So that's just...
and I'm sorry, can you show one more time where exactly we are in the spiral arm?
We are where you see a zero.
Yep.
So that's up top.
Okay, yep, on the top right is where...
Top right, yes.
So are we in a spiral? We're not in a spiral arm right now.
We just moved through a spiral arm, and we are experiencing over the last 30 million years, we have had a glaciation. A glaciation means that we have ice sheets on Earth, and Antarctica, it glaciated about 34 million years ago.
So that's when Antarctica was formed, about 30 million years ago.
The ice sheets.
The ice sheets.
Yes. So 40 million years ago, or 34 million years ago, that's when that happened. So the ice sheets, they sort of formed.
So when the dinosaurs were walking around, there were no ice sheets down there?
When the dinosaurs walked around, they disappeared around 65 million years ago, and that was very warm. There was hardly any ice at all.
Wow.
But of course, I mean, the first dinosaurs came 250 million years ago, so
right.
they had a long period on Earth.
Right.
But in the end, there was no ice.
So we're technically in a glaciation period right now, and we're exiting it.
We are in a glacial period, yes.
And we are about to get very warm. Not probably, I mean, we're talking geological timeframes here, but...
we will go in through, in maybe 30 million years.
In about 30 million years, it's going to get very hot.
The weather forecast for 30 million.
And so how long do you think it will take before like the South and North Poles are completely melted?
That's a good question. I mean, it comes... I mean, you can see here it's over some millions of years, I guess, that you have a change if you look at it.
Yeah, so...
And also, I mean, when you are, if you look at the 50 million years when you don't have any ice sheets, the sea level is of course much higher.
Right.
So, and you have the continent are flooded. So, the U.S. was flooded. Parts of the U.S. There was no Florida. Florida was underwater.
About a year ago, I got hit with a text about an unpaid toll. And then when I went to go pay it, it ended up being a scam. And this would not have happened if I had been using Cash App. And that's because Cash App prioritizes trusted individuals. Keeping your money safe from fraud deserves to be a priority, and Cash App treats it that way. With Security Lock, Cash App requires a successful Face ID or biometric authentication to access your account. It's like your money is protected by your own personal bodyguard, even if your phone is lost or stolen. Plus, if you're about to send money to someone new and Cash App notices something fishy or looks a bit off, or you might be falling for a scam, it'll send you a warning before the money is sent to confirm that everything looks right. Turn on Security Lock in your Cash App settings today and pay attention to scam warnings to keep your money safe from fraud. And you can learn more at cash.app/security. Moving your money should be simple, but it should also be safe. And that's why I like using Cash App. New Cash App customers can earn $10 if they use the code SECURE10 in their profile at sign up and send $5 to a friend within 14 days. Terms apply. Cash App is a financial services platform, not a bank. Banking services provided by Cash App's bank partner. Visit cash.app/legal/podcast for full disclosures. Now, there was a moment in the documentary that you guys did where they were like looking at the sediment layer near the Dead Sea. Is that right?
Yes.
And there was like some cliff sides near the Dead Sea, and you guys were studying that. What exactly were you guys looking for there?
It was just an illustration of past climate that you can see in these sediments and how it's changing. And I think there's someone who has studied it in more details and showing that there are some correlations with climate in the sediments.
Now, is there any specific correlation between supernova activity and like biological life on Earth?
Yes, and that's one big part of my work now that I've been working on.
And is that all tied back to climate?
It ties back to climate because the temperature changes that you have here is maybe 10 degrees. Global temperature. Remember, we are talking about maybe 1 degree with global warming, but 10 degrees. It's so big that it will have impact on climate.
10 degrees.
Yeah, these changes are just huge that we are talking about, and I can show you. I mean, I think it's completely fascinating with this. So if you go to 37, so. This is just to say that climate is quite important because at any time here on Earth, nutrition has been a limiting factor.
Yes.
So nutrition, that's phosphor, iron, and nitrogen, and so on. It's all things that life is needing. And there is this, if you have a certain bioproduction, that is, you have life, then life would rather uptake carbon-12 than carbon-13. 1% of carbon is slightly heavier. It's a stable isotope. But carbon-12, and this is important because it gives us a way of saying how much biomass there was on Earth at a certain time. So when you have sediments, and you can have inorganic sediments that fall down on the bottom, and that makes all these sediments that you see, we'll see them just in a second. Then you can imagine if you have a large biomass, that means that there's more carbon-13 in the oceans than if you have a small biomass. So by measuring the ratio between carbon-13 and carbon-12, you can say something about how much biomass there was on Earth at a certain time. If you go to the next slide.
Wow.
You can... Is that the next one? Oh, it's just... Yeah, one more time. Yeah. So this is the Grand Canyon. So the idea, what you see here is all these layers are past times where you had an ocean bottom.
Oh, wow. Okay.
And then you can, geologists have then gone and measured this carbon-13 relative to carbon-12. And that estimate the fraction of organic matter that is buried in sediments. So this measure with the isotopes, it unlocks how much organic material there is, and that is how much life there was in the oceans at a certain time.
Oh, wow.
So if you go to the next slide, and so what you have here is my reconstruction of cosmic rays over the last 500 million years. And you can see there's some different curves, and these are different databases that I have used, but they all show more or less the same thing.
Okay.
And that is the change in cosmic rays over this time. So what you see here has nothing to do with the Earth. It is astrophysics, pure astrophysics.
Pure astrophysics.
So if you press the bottom, you will see the change in. This is the fraction of organic matter in sediments over that period of time, and you see a remarkable correlation.
Whoa.
Holy crap.
That is wild.
So
the more of this astrophysics activity that we get, the more organic matter we get.
yes.
That's correct?
Yes. It's the fraction of organic matter in sediments. And the idea is, if you press one more time, I think that something will come up for explanation there. So if you have a high cosmic ray flux, you have a larger bioproductivity, and therefore also a larger fraction of organic barrel into sediments.
So the hotter it is, the more organic matter you get.
The colder it is.
The colder it is. So the higher cosmic rays... Okay, yeah, I'm thinking when the word ray breaks my brain. I think sun rays.
Yeah. No, but it is this sign thing is problematic. But it seems as if nature can figure it out.
So the lower the temperature, the more organic matter.
Yeah, and why is that? It's because that when it's cold on Earth, you have a larger temperature gradient between the equator and the poles.
Okay.
There's a larger temperature difference
between the equator and the poles.
And that means that you have stronger winds. So if you have stronger winds, you have much better circulation in the oceans of nutrients. So then you can deliver nutrients to the life. And that's why when you have a colder climate, you can get more. So it helps delivering the nutrients.
So even though it would probably be less organic matter on land, though, right? Because it's very cold, and there's not much. There's no vegetation.
It's something I've been working on. It's not published, but it seems as if it's completely opposite on land.
Wow. So it would be so if it's a very warm climate and it's lush on land and fertile and lots of life, that would mean it would be the opposite under the oceans?
Yes, because then you have a smaller temperature difference between the equator and the poles. There's not much mixing in the oceans. It gets much more layered, so you don't get the nutrients circulated.
That is wild.
So this, this I think this published it in 2021.
Mm-hmm. So those layers that you're measuring, the difference between carbon-12 and carbon-13, that's specifically for the organic material, the organic mass that's under the oceans.
Yes.
Now, how do we measure what's above the oceans?
We can't really measure it that the same way.
No.
So that's a problem. So what I've been doing is trying to model it based on photosynthesis, and you have how much energy that goes in. You have to see how much CO2 there was in the atmosphere, how much oxygen there was in the atmosphere, and how much water was available. And you put all these things together, and you can try to at least simulate the organic amount on land. But I don't have any view graphs of that here.
So this is like completely blowing my mind. Why isn't this more popular, and why aren't there more people talking about? This is the first time I've heard anything like this.
Oh, but I'm not even finished.
What else should we go through?
But when I give talk to general public, they're very happy about it. They like it. So people who don't have an interest in global warming are happy about it. But you see, if this is
people don't have a financial interest in global warming.
Exactly.
Right.
I mean, the whole politics about global warming has been.
Were you aware of how ideological and political the global warming and the climate narrative was before you started looking into this?
I had no idea. It came as a big surprise for me. I mean, I had simply, and it changed my life completely. So in some quarters, I'm a heretic because I say that. That there are other things that might be important. So if you say that things like cosmic rays and solar activity is important for climate, it's not welcome. I mean, if you look at the IPCC and you look at the report, you can see that the amount of, what they attribute to solar influence is more or less zero. Zero. I can
now, for people that aren't aware, what is the IPCC?
It's the International Panel on Climate. They're one that, advise government about climate change and how, dangerous anthropogenic global warming is.
Now, didn't they say that water vapor has a bigger impact than CO2, the IPCC?
Well, I mean, water vapor is, of course, the most important greenhouse gas. It's the one that raises the temperature, almost 30 degrees on the Earth. But it's not seen as a greenhouse gas, because they're mainly looking at. It is greenhouse gas, but they don't look mainly at anthropogenic things. I mean, we can show you the IPCC report. If you look at number 3, if you can, So here you see the different.
This is the latest estimate from the IPCC.
Yeah, something like that. But you can see at the total effect of anthropogenic is about between 2 and 3 watts per square meter.
Which one is anthropogenic?
It's the one. It's
one from the bottom.
Yes, the one from the bottom, the red one.
Yep.
And then you can see there is a little one where it's solar.
At the very bottom. It's like 0.
It's
solar. They're saying solar has 0.
It's 0 since 1750 until present, and that the reason they're saying that is, of course, they're saying that solar irradiance is not changing. They're not really taking into account things like cosmic rays. The cosmic rays, if you put it in, I would say I believe it will be around 1.5 watt per square meter. So it will be comparable to the whole anthropogenic thing, and that's why.
So you think that? So you're saying you believe that cosmic rays have the same effect as the total anthropogenic effect on climate? It's about equal?
Yeah, maybe slightly smaller, but 1.5 watts is on that order. I should say that, we have done a lot of work. What we need to do, and what I was hoping to do, was to put all these mechanisms that we have now discovered, and we now know how it works, and how to put it into a global model where we both have, cosmic rays and greenhouse gases, and then run a model just like these models that they use in the IPCC to see how important is this change in clouds. Because that's a natural thing to do. My problem has been it's been impossible to get funding for doing this work. And that's my general problem. It's been very, very difficult to finance.
Now, who funds all this stuff?
Well, these are government funded. All of
government
this,
funded.
yeah.
And the people that are a part of this IPCC,
the funding is. That's the thing. If you go before the IPCC was formed, there was very, very few people doing climate science. But after you put the idea up that it was a big problem and we are, it might be a disaster in the future and so on. A lot of money has gone into it. I think it's, to the research, it's several billions in the US a year.
Several billions?
I think it's billions, yeah. It's a lot.
And where does that money come from?
From you.
It's from the taxpayer. It's government funded.
Yeah, it's got the government. I think.
Wow.
It's something you have to check, of course. But I remember seeing a report where those numbers were mentioned.
So aerosols goes backwards.
Yes, but that's the thing is that if you put in more aerosols, then you produce more clouds, and then you cool the Earth. So they're conceding that. Yes.
They're conceding the aerosols and clouds to cool the Earth. Now, what did you make of this proposal? I think it was Bill Gates proposed on putting reflective particles in the atmosphere or something to reflect the sunlight. Are you aware of that?
That's called geo-engineering.
Geo-engineering.
Yes, I'm not sure it will work, but I don't think it's necessary to do. The good thing is that when you stop putting particles in, the effect stops very fast.
When you stop putting the particles in. And also those particles would fall to the ground eventually, you would think, and that would create lots of pollution.
Would rain out.
It would rain out, right?
Yeah.
And how would that affect like the natural estuaries and like the sea life and stuff like that?
Nobody knows. It's very difficult to say, but I think it's very difficult to sort of seed the whole Earth. I think the idea was to have some ships maybe in the Pacific pumping up particles. You saw the ship tracks.
Yeah.
So it's a similar idea.
Okay. Yeah, and I actually believe Bill Gates has like rescinded that. He has been traditionally like one of the biggest proponents of this whole climate warming narrative. And there was something that came out recently, Steve, maybe you can find it, where he's gone back on that.
He's gone back on it, yes. But it's also because they need a lot of energy for AI now. So. And you need,
So he's hopped to
and
a
you
different...
cannot get it from solar and wind.
Right. No, they need way too much energy to power that. Solar and wind would.
Do you want to see one more thing? I have a few more things on the long time scales, which I think are completely fascinating.
Yes, please.
So if you take 41, so what you have here is, we just look at the last 500 million years, which is the very, very short part of the right of this figure. But what you see here is a reconstruction of the star formation going back 3.5 billion years.
Wow.
And this is... it's showing that, for instance, for around 2 billion years ago or something like that, you had a burst of star formation. Mm-hmm. Then you had 1 billion years where it was very quiet in the galaxy, in our Milky Way, and then you had a burst again around 1 billion years ago. Mm-hmm. And then you get to the 500 million years, where I just showed you how it looked. Now, the thing is that you have had photosynthesis during the last 3.5 billion years on Earth through algae and so on. So you can actually look at this exact same thing, the amount of organic material buried in sediments. And this is the geology. So if you take the next, Steve, there, that is the change in the fraction of organic matter in sediments. And
wow.
And you see the correlation?
Wow.
With the star formation.
Yes, with the star formation on top. So you see a beautiful correlation. Now, there is one thing I want to mention about...
So star formation means more cosmic rays.
Exactly, yes.
Which means colder temperatures.
Yes.
And which also is, according to this graph, means more organic sediment layers.
Yes, more. Yes, organic sediment layers. You're right. If you press the bottom,
Are we talking in the ocean or on land?
This is the ocean.
Ocean, right. Okay.
So it's oceans again. Now the thing is that if you look at photosynthesis, everybody knows that when you combine water and CO2 and sunlight, then you get a sugar, glucose. And that's part of what goes into the organic part, and that goes into life. And then you produce oxygen at the same time. But if you now take the organic material and you just leave it on the surface of the Earth, the reaction will go back again, meaning that the oxygen, there will not be produced any oxygen. So in order to produce oxygen in the Earth, you have to bury the organic material. So when you bury the organic material, then you are left with the oxygen. So the curve over there, the bottom curve, it is actually also the oxygen production rate over that period of time.
Wow.
So it means that you can see there's a period around 2 billion years ago where there was a lot of oxygen produced. It doesn't mean that necessarily that the oxygen went into the atmosphere, because at that time you had a lot of iron in the oceans, and the oxygen was stuck to the ions and became this red sediments that you have called iron bands. But if you go to around 300 million years, we had actually maybe closer to 30% oxygen, whereas today we have about 21% oxygen in the atmosphere.
Wow.
And the other thing, why it's so important for life, is that oxygen is really needed if you want to have complex life, because that's what transports energy around inside complex life.
All right, Steve found the Gates from Axios. Gates stressed the difference between supporting research and advocating development.
Deployment?
What do you...
I don't know.
This is about...
where he draws the line on dimming the sun. Bill Gates says he would support deploying artificial cooling technologies to lower global temperatures, but only if the planet hits a so-called climate tipping point. Yeah, but he recently went back on this, Steve. You can find another article that was published probably recently in the last few months where it's basically saying that Bill Gates abandons his climate change push or whatever. You'll be able to find. Yeah, the problem with things like this is people, they like to latch onto these hot topics and find ways to benefit from them. Find ways to capitalize on things like this by turning them into an emergency, and find it because it benefits them in some specific financial way. That's the problem with all these things, right?
Yeah.
Whether it be climate, whether it be medicine, pharmaceutical stuff, or geopolitics. You name it, people can manufacture these emergencies, get people to panic so they can justify spending money or making money somehow.
Yes.
Yeah, as you learned the hard way.
Yeah, that's true.
Has there been any legitimate pushback against this from people? Like, has anyone ever sat down with you and had a reasonable conversation with you and explained to you why they don't take this stuff, your research, seriously?
I would say, there has been some reasonable persons, but there's never been anyone there's never been anyone saying that it's all wrong. The thing is that when we found these things experimentally, I think we published it around 2007. Then from 2009 and onward, people tried to put it into global models. So they tried to mimic this idea that cosmic rays produced some extra aerosols, these small, very small particles. And then the idea was to see if they could then grow to become cloud condensation nuclei. And if they can do that, they could affect clouds. So they tried to put this into these models. And I think 6 or 7 groups, they all got the result that they didn't grow to cloud condensation nuclei. They got lost before. And from that has really been the main critique that these small particles do not survive to cloud condensation nuclei. Mm-hmm. And that sounds like a really serious problem if that was true. But in 2017, after 4 years of experimental work, because I didn't believe that it was true that there was this problem. One of the reasons is that we can do some observations, and I can show you observations showing that these particles are actually growing to become cloud condensation nuclei in the real atmosphere. So everything works out there. It's only in the models it didn't work. But the question, of course, why? And we spent almost 4 years, and what we found out in the end was that the cosmic rays are not just producing small aerosols. They are also assisting the growth of aerosols, so they can accelerate the growth, so they grow faster. Mm. And when they grow faster, the chance of being lost is smaller. And we have tried to put that into a global model of the same kind as other people have been using. And when we do that, we start getting things that are very close to the observations. So the reason that all these groups did not find this effect is simply because they didn't have the right physics in the models.
Oh, interesting.
So, yeah, I mean, I can show you so many things. Let's look at what number is that? Number 20. If that should come up. Yeah. So
coronal mass ejections.
Yes, coronal mass. So you have the sun in the middle, and what you see is solar wind that all of a sudden you have what we call a coronal mass ejection. It's
like a burp. The sun burps.
Yeah, you could say that. And it burps out a magnetic plasma. So you have magnetic field lines that are sort of open up. Mm-hmm. And if that hits the Earth, it screens against cosmic rays. If you press one more time, you will see one event. So
it blasts cosmic rays out?
Yes.
Okay.
So this is what you see here. These are days of the year, and you can see that you have this effect on the cosmic rays. These are measured on Earth, and you see there's a big drop all of a sudden in the cosmic rays.
Yep.
And it lasts about a week. And then the plasma sort of dilutes and move out through the planets, and the cosmic rays are getting back. But this is what I call the natural experiment for testing this idea. So when we have these events, I can then look at satellite observations of Earth's clouds and see if anything happens.
Oh, yeah.
So this is what I've done. So if you look at the next slide. There. So I have 15 days. I mean, if you take the first one where it says aerosols, then you have 15 days before the minimum in cosmic rays. This is this red dotted line.
Yep.
And then you have 20 days after.
Right.
And the black curve is the change in aerosols. And you see there's a dip in the aerosols where the maximum around 5 days later.
Right. 5 days later, you see the dip.
Yeah, and why is it 5 days? It's because that's the time it takes for the aerosols to grow, to become cloud condensation nuclei. So it takes a little time for the small aerosols to grow and become cloud condensation nuclei. It takes about 5 days.
Oh, wow.
So, and then you have three independent data sets which measure cloudiness or clouds. And you can see that there's a minimum in all of them around 5 to 10 days after, or 5 days.
That's fascinating. So when we have these big CME events, these cosmic sun burps or whatever, we see a super big drop globally with cloud coverage.
Yeah, when you say super big, it's only about 2%.
Only 2%. Okay.
Yeah, but 2% is actually similar to what you would get over a solar cycle. And it is on the order of, this 1.5 watt per square meter. Remember, we talked about the IPCC, and it was about 2.5 watt, which is the anthropogenic. So
yes,
we have 1.5 watt changes here.
Oh, wow.
And we even get, locally, we can get up to 4 watts changes in
specific locations.
Yes, in the Southern Ocean. Because that's where you have very clean. This effect is best over the oceans, and that's because you have very few aerosols there. Mm-hmm. So if you put a few extra aerosols in, it makes a change. It makes a change in the number of cloud droplets. If you go over land, you have so many aerosols that even though you are producing clouds, it's only a fraction of them that are being activated to become cloud droplets. So if you put some more in, it doesn't really change things.
I see. What is the there's some sort of like an anomaly that's over South America, like a geomagnetic anomaly?
Yes, that's because the Earth's dipole moment of the magnetic field, it sort of shifted a little bit, so it's slightly weaker over the South Atlantic. So you have more cosmic rays coming in there, and it's actually been a problem for some certain low orbiting satellites because they get much more cosmic rays.
Oh, really?
There, yeah. So
how do the cosmic rays affect the satellites there?
It can go in and affect the electronics.
Oh, negatively.
Yeah.
Even though it doesn't mess with human beings, it messes with electronic stuff.
Yeah.
Wow. So in that area of South America where we have that like hole in the magnetosphere, essentially what it is, because of that, it's
just weaker.
It's weaker. Okay.
It's just weaker. It means that more cosmic rays can come in. The Earth's magnetic field.
There's a lot more clouds there?
We looked for it. It's very difficult to. Because here you have globally 2%. So
right.
It's very difficult to see.
One of the biggest growth hacks in business is when you finally realize you don't have to do everything yourself. We've used Upwork a lot over the years, from everything for editors, designers, architectural designers, and all kinds of different specialized trades. Even these windows in our set were designed by a freelancer from Upwork. And that's what I mean. You can bring in extremely skilled specialists for any type of task you need, and all without turning it into some big, laborious, elaborate hiring process. Upwork connects businesses with freelance professionals across software development, AI implementation, marketing, design, business operations, and way more. You can browse profiles, review past work, so you can hire with confidence and get started super quick. And with Business Plus, you can access the top 1% of talent on Upwork. AI-powered shortlisting delivers a curated list of freelancers matched to your goals in under 6 hours and without endless searching. Contracts and payments are handled all in one place, so it lets you focus on running your business instead of dealing with logistics. Visit Upwork.com right now and post your job for free. That's Upwork.com to connect with the top talent ready to help you grow your business. That's spelled UPWORK.com. Upwork.com. And is it true that the poles of the Earth are moving?
Yes. Oh, the poles of the magnetic poles, yes.
The magnetic poles are moving every year by quite a bit, right?
Sometimes quite a bit, yes. And especially if you are on the verge of a what do you call a switch, where you switch the polar.
Like a full flip?
Yes, you can have a full flip that you have. Typically, I said the last time was about 700,000 years ago.
700,000 years ago.
Then there was a near flip, I think 39,000 years ago. You can see that also.
Really?
And you can see it. Remember, the cosmic rays comes in and they produce isotopes. The isotopes then might fall down on snowflakes and on the ice, and then you can measure and you can see that at a certain time there was much more cosmic rays coming in, and that's because the Earth's magnetic field was all of a sudden weak.
Whoa. So how many years has it been since? Okay, so it's been. You think every 700,000 years there's a complete flip?
There is a flip. It's not exactly 700,000
Roughly?
years. Roughly, yeah. I mean, you know that's a way that you discovered the continental drift.
I had no idea.
No, because when you have the continent in the Pacific, for instance, they are moving out, and it's what do you call lava? It's
like volcanoes?
Yeah, volcano, and
the lava comes up through like the
and then the plates are moving away.
Right.
And then the magnetic field that you have at that time is sort of stored in the lava when it hardens. So then you can see if you go with you measure the magnetic field orientations over the bottom, you can see that all of a sudden it flips, and then it flips, and then you can see there's about 700,000 years between these flips. So there was something that was discovered in the 60s. And that was, Wegener. He was the one that proposed it in the 1920s, that there was continental drift, and he was ridiculed for a long time.
So if that magnetic flip happened, how long does that take?
It takes about maybe 5,000 years.
Oh, wow. Oh, that's not very fast. That's very slow. I thought it was like a one-day thing.
No. It takes no.
So it's not something that anyone would notice. It's not like a catastrophic event that happens.
Not as such, no.
Okay. See, when I hear of this happening, I thought it was like the Earth's crust or something flipping around the core.
Well, it is, of course, the liquid movement inside that are changing, yes.
Is it possible for the actual like outer shell of the planet to become disconnected from the interior part of the planet and move across, like move?
Well, I mean, the plates are moving, but that's very slow, what is going on. So, and I mean, we have a solid core. In the most inner part is a solid core.
But the layer between the core and the surface of the Earth, there is a magma, right? Like a liquid,
yeah.
Okay. So it's never happened to where like the actual surface of the Earth has like abruptly changed or moved or something like that.
Not like that.
Not that we know of.
No, but I mean, the continent, if you look over millions of years, they have been moving like crazy. So geologists say that India, for instance, has been moving, like a speedboat up through the Indian Ocean at that time. And that's why, and it burst into Asia, and that's why you got the Himalayas. They're so high.
Right.
So they're quite recent.
That's fascinating. So, okay, wow. So it seems like if it's true that what you're postulating here is that the cosmic rays and then the solar activity and all the supernovas throughout the Milky Way, also in correlation to where we are within the Milky Way Galaxy, whether we're in the arm or whether we're in between arms, has an equal effect on the overall climate of the Earth. Yes. Compared to what humans are producing.
Yeah, I mean, on these timescales that we've been talking about, I mean, it's huge. It's very, very big changes we're talking about. And it's big changes that are not just changing climate. It has been very important for the conditions for life on Earth. So that's it.
Well, depending on how much activity is happening in the Milky Way Galaxy, it can have dramatic shifts, something on the effect of like that no humans could ever produce.
That's true. I mean, if you go to,
it's interesting that you put it this way. Like, the way you lay it out is very interesting. It's very compelling because, like, most people, the way people think about things nowadays is binary. Like, it's either this way or it's that way. It's not. There's no room for nuance and things like this. But what you're showing is like, yeah, like human beings are contributing to CO2, but what you're showing is how much of a real effect, like how dramatic the effect of these cosmic rays and the solar activity can actually have over billions of years.
Yes.
And, we're just this little blip on the geological timeline of the Earth. And it's important to have that perspective on it.
I think it's deeply, deeply fascinating when you look at these. I mean, you said billions of years. There, I showed you a figure where you saw changes in star formation over billions of years. The reason that you have star formation over billions of years is not because of spiral arms. It's because the Milky Way, you have some what we call dwarf galaxies that are getting close to the Milky Way, and when it gets close, it induces star formation because of the tidal effect on the gases. So
it's other galaxies running into the Milky Way Galaxy.
Yes, if you go to number 43, I can just show you one example. You have the Milky Way, and then what you see is the path of what is called the Sagittarius, a dwarf galaxy. And on the insert, the curve there, what you see is periods when it induced star formation in the solar, in the Milky Way. And you see around 6 and 4 billion years ago, there was a large interaction between the Milky Way and this dwarf galaxy. And that is actually also
6 billion years ago.
Yes.
That's so crazy.
But that's actually also when the solar system was formed. So it might be that this event was part of why the sun was formed.
Oh, wow.
But then if you then move further on and you get to 2 billion years, then you see there's a big burst of star formation because you had an interaction again. And 1 billion years, and these two peaks, they fit very beautifully with the figure that I showed you before. So
2 billion years ago, it hit the other side of the Milky Way.
It might have hit, yes. And then it induces star formation, and on these timescales, it's in general it produces a lot of star formation in the Milky Way.
Oh God, this is so wild. And the Big Bang is 14 billion years ago,
something like that.
What is the story? Are you familiar with this this data that came out in like the last year? Maybe it was longer than a year ago, but I discovered it a year ago, where somebody wrote a paper about how they found some super old or late galaxies or something, and something about measuring the redshift.
Yeah,
this would have pushed back the Big Bang or something like this.
Yeah, I'm not sure where things are standing at the moment, but there are some that might be some revisions to how we understand how things started. I mean, you have Roger Penrose, for instance, Nobel Prize winner. He's talking about cyclic universes where one universe it goes back and forth, so it recreates itself over and over. So there are many ideas, but it's sort of on the limit of what we can comprehend with the data we have now. But it's fascinating.
Yeah, it's I can't imagine it's a very easy process to revise history like that. That's been sort of, been written in stone, for lack of a better way of putting it, right? It's people don't like to change the past, like based on new data. When we find new data, it's not, when has it ever happened that we've revised history books? I don't know.
I mean, it should happen. In science, it should happen at some point. Of course, people who have been working on things and believed it a certain way, they will, of course, want to defend, and they want to, it has to be good evidence in order to, contradict a certain theory.
Because you have, there's jobs that are at stake, right? People have jobs to defend, and they want to. I would imagine, I've never been in that world, but I would just from like what I've experienced with people on this podcast, there's a tribal mentality where it's like, I want to fit in with the other people that think like me. Yes. And it's like this in group in academia.
Science is done by people. And of course, you have some idealized idea about how science is done and so on, but it's done by people, so sometimes they don't behave as they should.
That's a very good way of putting it.
Yeah.
Do you think, like with other colleagues that you've worked with in, what's the university you work, or you no longer work for the university?
It's the Technical University of Denmark.
So, like with the people that you have conversations with, at this university who may be like on the periphery of your studies, have you noticed that this is more like an ideological thing, or it's not talked about, or is it strictly financial, or is it both?
I would say many of my colleagues, because it's an astrophysics group, they're interested in astrophysics. I think most of them have no, stake in climate at all. So they just think that if some of these astrophysics things are really important for what's happening on Earth, I think they think it's interesting. But if you start. If I go to the University of Copenhagen, where people are working on climate and they are climate scientists, and some of them are working for doing work for the IPCC, the International Panel on Climate, they have some stakes in this, and that seems to be. It's not founded in, just in science and rational thoughts. There are other things, and there you see that it's people that are doing science.
So the IPCC funds a lot of the people.
But they don't fund people as such, no. They just nominate people, and then they work for them, and
they nominate scientists and then bring them into.
Yes, and then they write certain chapters and make some assessment of the state of climate and all the research that is being done. And when you write these types of large governmental reports, a lot of it is how you phrase things, what you want. So even though my stuff is in this, in the IPCC reports, they do mention it and they have some chapters on it. They used a lot of time saying that all these people who couldn't get it to work in their models, that is the state of this. So they're saying that there might be an effect, but it's not important.
Right. The problem with it, high level, is that this is such a complex thing to understand. This whole topic, there's so many moving parts, right? And there's climate, yeah, and it's tied into everything, like with geological, with astrophysics, and chemistry, all of this stuff, and chemistry. Like just what you've showed me so far is blowing my mind. And 99.999% of human beings on this earth who are aware of climate change, they don't know anything about this stuff, yet they have an opinion on, based strictly on political. Like you could take the political divide just in this country and you can just say, tell me what political side they're on and I can tell you what their stance is on climate change.
Yeah.
And they have no understanding.
No. And it's also because it's difficult, right, to know all these things.
Super difficult.
Yeah.
Right.
I mean, it takes some efforts in order to get a hold of and really make a good opinion about this.
Mm-hmm.
Do you want to see more on how it affects life?
Yeah, definitely.
Okay.
Let's do it.
So, what I want to discuss now is, we talked about that we had a huge effect on climate, and the climate had a huge effect on the amount of biomass that we had on Earth.
Mm-hmm.
So the question is, has it any influence on the macroevolution, that is, the life forms that we have had on Earth?
Mm-hmm.
And the life forms, I mean, how do we know history back in time? It is from fossils. So if you go into sedimentary mountains that you have here, this is again Grand Canyon,
Mm-hmm.
you can go into different layers and then you can find different types of animals or fossils.
Mm.
And these fossils, it's something that has been investigated by biologists and paleontologists, I think they're called. And they have put all this data in huge databases. So you have all this information about what kinds of animals you have at a certain time. And the interesting question is, why has life changed? The number of, you call it the diversity, why has that changed as a function of time?
Mm-hmm.
So what I did is I took some of these databases. If you look at the next slide here. So here we again have the last 500 million years. And what I've done is I look at the number of what we call genera. It's just above the species level. Like, a cat and a lion, that's the same genera.
Right.
So what you then count here is the number of genera, and you can see that over the last 500 million years, there are some changes. You see that there are sort of two maxima, around 400 million years and one around 300 million years,
Mm-hmm.
and then there's a slow increase until our modern time.
Right.
And the difference between the three curves is simply the way that you have extracted the data from these databases is done in slightly different ways, but they all show some similarities in the data,
Wow.
as you can see. So the question which is asked here is, why are there these changes? I mean, why is the diversity or the richness of life, why has that changed over time?
Mm-hmm.
And there's been many ideas about this. What I want to show you is that you can actually, I think you can explain it with just two things. One is supernovas, and the other has to do with the area of what we called shallow marine margins, shallow marine, the shelves.
Sea shelves? The continental shelves?
Yeah, continental shelves. So if you go to the next slide. What you see here is about 100 million years ago in the Cretaceous period. And you can see you had much higher sea levels.
Whoa.
And therefore, a lot of the continent were
Florida is gone.
Yes, everything is flooded. And a large part of the U.S. is flooded too. And the light blue areas, that is where you have this shallow water.
Right.
And where you have the shallow water is really where most life in the oceans is.
Oh.
And then in biology, it has turned out that if you have a larger area, you have more species. So if you have a region with a larger area, then it seems every time...
Land area?
Well, area also in the ocean.
Okay.
So if you have a larger area, you have more species. So if you have a small area, you have few species. If you have a larger, it scales with this area. So that's one thing. So if we go to the next slide. So okay, so yeah, just hit if you no, yeah, okay. So yeah. Yeah.
Okay.
So this is this low area, and the idea is that it's there where you have all the most of the life. The deep part of the oceans is more like a desert.
Mm-hmm.
So there's very few.
Not much life.
Much less life. Yeah.
That's why all the big fish that are out there, the pelagic fish, like the oceanic sharks, they're like they're scavengers. They're eating anything and everything.
Yeah, that's true. Okay, so I say that the diversity is somehow proportional to this area. So we go to the next one. So what you see this top, you can see how the continent has been drifting as a function of time.
Which continent is that in the yellow?
I think it's South America. You can see it now.
Oh, I see. I can see it now. Yeah.
So, and you see that we get up to the modern time, and everything looks like the map that we know today.
Right.
But if you look at the curves down under, you can actually see how the area has been changing as a function of time. So there was a period where the seashells were not that big.
Mm-hmm.
And then there's a period where it's big. If you go to the next one, it's just... So I say that the diversity is proportional to the area of this shallow water times the supernova. So if you just press it one more time. So if I now divide by the area over on the other side, then I have one part which is only supernova, and the other one is only diversity divided by area. So the curve up there is the diversity, and I divide it now by the area, and go to the next slide. Yeah, just go to the next. Like this. This is the change in cosmic rays over this period. And now I will put on top of that the diversity normalized with the area. If you plot that.
Okay. Whoa.
So what you see is a remarkable correlation over
so much more sea life when the cosmic ray activity is high.
Yes. Diversity, richness of life, yes.
Why do you think it is that Earth is the only planet in the solar system with life?
There must be some special conditions that... it could be that there has been life on Mars.
That's what a lot of people say. A lot of astrophysicists say that... they say it could have originated on Mars.
It could, yeah.
And then spread here.
That's a possibility, but it's amazing that how difficult it is to determine whether there's been life on Mars or not.
It's crazy too. Like we think, we look everywhere for life all over the universe. We try to imagine, how many billions and trillions of planets and solar systems and, galaxies there are. But the one planet that we know of that's completely teeming with life, the most logical place to look would be our next door neighbor.
Yeah.
It's just crazy that it's a completely barren wasteland.
But if you go to Venus, it's, horrible.
Oh, it's hell, right?
Yeah. It's hell on Earth.
And people believe that there could be life in the clouds of Venus, right?
Yes, I know scientists who...
they're studying that.
Yeah, so I've suggested it. I don't know how to study it, but maybe, yeah.
Mm-hmm. And I guess the idea is that, and I could be way off base here, but that the planets that are orbiting the sun are slowly moving outward. And who knows how long ago Mars could have been more in line with where Earth is now. Does that sound right?
That I don't know.
Okay.
One of the reasons, there's one interesting, we have the moon. Mm-hmm. The moon is, orbital locked to the Earth.
Yes, that's a huge part of it.
And that makes stabilizes our rotation axis.
Right.
So if we didn't have the moon, our axis would wobble like this. And, having complex life would probably not be possible.
does Mars and the other planets in the solar system have a similar axis wobble like the Earth that we know of? Are you aware of that?
They have some wobble, but I'm not sure how big they are.
Also, the Earth, as far as I'm aware, is the only planet that we know of that is like has the specific distance between the moon and the sun to where you get that perfect eclipse.
Yes, that's true. So
from what I understand, that's like extraordinarily, almost impossibly rare.
Yes, it is rare. And it's also rare that a planet have such a large moon. So the moon is really large. Mm-hmm. I mean, if you look at Mars,
and most moons are like potato shaped, like weird oblong, not perfectly circled.
Yeah, but that's because they're very small. So gravity cannot form
it.
The sphere. Yeah.
Right. That's bonkers.
So when I found these things, I mean, I hardly could believe, what I was seeing. So it's...
I can hardly believe it.
Yeah.
So what is your plan next? Like, what other sort of studies or investigations do you plan on doing to corroborate this even further? Is there anything more you can possibly do?
Well, I mean, what I wanted to do, which was to take one of these global models and then show that it actually also important over the last 100 years. That's one part. So the idea is to incorporate this mechanism with the cosmic rays and the effect on clouds into a global model where you then also have greenhouse gases, and you have everything. And then show that it's actually also important in present day. It has some importance, but it might not, it doesn't mean that CO2 is not also important in some sense. But it could be that the climate sensitivity to CO2 is smaller than what you get from climate models in general. I mean, you know that if you double CO2, then you, from the IPCC, the International Panel on Climate, they have made an estimate that the temperature will increase between 2 and maybe 5 degrees.
If we double the current CO2?
Yes. If you have a doubling of CO2...
Now, it doesn't sound like a lot, but would that be a catastrophic effect for humanity?
That's what they're saying.
They're saying 2 to 5 degrees would be...
Yeah, 2 to 5. But... this temperature change is not from CO2 alone. It is simply because you imagine that if you increase the CO2, then it also changes the amount of water vapor and the amount of clouds in the atmosphere. So most of the warming that you see from this model is because they think that you have less clouds in a future climate. Therefore, it gets even warmer. You have more water vapor, so it has more greenhouse gas from that. So these are what we call feedback effects.
Yes.
Positive feedback. So it increases the temperature. The direct effect from CO2 alone is only about 1 degree.
Right. But you're saying that everything else is connected to it, so it's going to have this cascading effect.
That's what the models are saying. But that means that most of the effect that you are seeing is not from CO2, but because you believe there is a large positive feedback from clouds and water vapor.
Oh, okay.
So you can imagine that if you now put in the cosmic rays, maybe the cosmic rays are changing things in such a way that the effect from CO2 is just smaller, and you don't have a large effect on clouds from the CO2. But it is controlled by cosmic rays.
Pull that mic in a little bit more so we can hear.
That you get an effect from cosmic rays because over the last 100 years, cosmic rays have been dropping. Mm-hmm. And there's been a drop in cosmic rays. So that could actually be part of the warming also. So you don't need so much warming from CO2.
Right.
And that means that the climate sensitivity to CO2 is smaller than what you get in these global model estimates.
Right.
And there's been a lot of studies, empirical studies, where they get that the climate sensitivity seems to be smaller than what you get. So it's on the order of, in the low end, so it may be 1 degree or 1.5 degree for a doubling of CO2. And if that is true, it means that this whole CO2 thing is less of a problem.
Yeah.
And we might have more time to find good solutions.
Yeah, they don't seem to be the world governments that seem to make this the big, this big, emergency out of the climate change thing. They don't seem to be practicing what they preach. When we're blasting off how many rockets every day, from right, 200 miles away from here in Cape Canaveral, launching satellites into, there's so many, there's like 60, 70,000 satellites orbiting the Earth at all times. Constantly the threats of nuclear bombs exploding, and throughout the 50s and 60s, how many nuclear tests that we were detonating all over the world. Like, what kind of effect did that have on the cosmic rays and all that kind of stuff? And as far as clouds and polluting the atmosphere, I know we did this thing called Operation Starfish Prime in, I think, the 60s, where American scientists, with the help of Nazi scientists, were detonating nukes in the upper atmosphere.
That's true, yeah.
Trying to see if they could blow a hole in the Van Allen belt or something. Who knows? It's just the amount of things that governments have been doing that have been just polluting and destroying the Earth is unimaginable. To try to blame that on people that are just trying to get by paycheck to paycheck, driving their gasoline-powered car and trying to impose more carbon taxes on them for that, it just seems like so counterintuitive. It seems so illogical.
I mean, it's going to be the economy that is going to be the thing that kills, solar and wind, because it's too expensive. And there are so many. I mean, you have Africa, you have India, you have China. They all want cheap energy, and you are not going to get it from solar and wind, unfortunately.
And as far as the global CO2 output, I think China is number one on that.
Yes.
Where China's like 30 to 40%.
Yes.
Of the total CO2 emissions. And then, America is like way down on that.
And the reason is that you are using gas, natural gas, right? Because the emission from that is much lower of CO2.
What has been your experience with, compared to your colleagues in this space, as far as like getting funding for your research?
That's been the problem. I mean, it's been nearly impossible for me to get funding. And as I said, 2021, the university tried to fire me first time. And then I was hired. I was not fired because of some protest from I actually don't know why they didn't fire me, but there were protests from some scientists at MIT and Princeton that supported my my research and said that it would be idiotic to fire it because it was important. But then they said to me that I had to find my own funding for my salary. And that's been nearly impossible. So I had to do all kinds of things, alternative things. So I had to find private funding for people who wanted to help me because getting public funding was nearly impossible. For the same reason that when I send in an application, it's usually sent out to other climate scientists, and in 99.99% of the time, these are people who believe that it should be something related to CO2, and what I'm doing is not something that we want to hear about. It's a shame that it's like that. Getting funding has been a big problem, and you cannot do research if you don't have funding.
Right.
in 2017, we did 4 years of experimental work, and after that, I couldn't get any money to do any more experimental work.
Was that the CERN stuff?
That was our stuff in Copenhagen.
Oh, okay.
And now they have confiscated my whole laboratory. I don't have the laboratory.
They've confiscated your whole laboratory?
Yes, I'm not allowed to go in there anymore. So, I mean...
What was their reason for doing that?
Well, I mean, the official reason is that someone in the institute had used, I think, 11 million Danish kroner. I don't know how much. That's maybe 2 million US dollars. Too much. So they had a deficit, and then they decided to fire people, and I was one of them that they wanted to fire.
Oh, wow. That was the reason they gave you, at least.
That's the reason they gave me, and I mean, in many levels. In 2016, I was, there was an international committee. I was a professor at that time, and I was up for becoming a promotion to it's called a full professor. Before I was just a research professor, and then. The head of the university, he simply cancelled the professorship, and I was demoted. So,
what was the reason he gave?
I never got a reason. I never had a reason why that happened. I mean, I could tell you so many weird things that happened to me, and it's because climate science is not normal science. I mean, I don't know if you have talked about. There are also American scientists who have lost their jobs if they have said the wrong thing about global warming. It's been so politicized, and the director of our university. He is, I would say, the only thing he goes up into, only talks about renewables and green energy and so on. So what I'm doing is probably not something that he likes as such. And so, I mean, so many weird things. Also, at some point, I got money from a foundation, and some research scientists, who head of sections in some large institutions. They contacted my foundation, who gave me money, and said that they should revoke my money because. I mean, I don't know, but they just want to. I mean, there's so many that have tried to stop what I've been doing. It's and it sounds completely awful, but what has been the good thing for me is that I've had this science that I could do, which I think, as you saw the results, I think they're so fascinating that whatever people thinks, because it doesn't fit into this global narrative about global warming and CO2. I mean, the whole part of what I'm talking about on these long time scales, it doesn't really matter because it's not related to CO2. It's the part where people think that it has an effect on what we're talking about with respect to global warming. That's why it's such a sensitive thing.
Do you have any idea who specifically are the forces behind this stuff, this push to get you shunned from academia and get all your funding revoked? Like, specifically?
I think it's individual people in some sense. I mean, I have no idea if there's any orchestrated thing. I mean, for the first time I got hired as a professor, there was a different, rector or president of the university, and he called me up to his office and said that he really liked what I was doing, and he didn't care if there was a protest or anything, because there should be, room. I mean, just what we would expect how science should be done. And then he told me that after he had, opened this position, he said that a number of, scientists had contacted him and said that they shouldn't hire me. Because of what I was doing, and they shouldn't have this kind of research. And I'm sure that the second time when I was up for this promotion, that some scientists have contacted the other new rector there, and he chose to close the position. So it's very difficult to understand for people who think that science is sort of a pure thing, and you just go try to figure out. And that's how it should be.
Trust the science.
Yeah,
the science is settled.
Yeah.
That's the phrase they use. The climate science is settled.
Yeah, and that's not science.
Right.
I mean, that's not a scientific, because nothing is settled in science.
Right.
It's always up for revision, what we're doing.
Now, have there been any specific people or universities or organizations that have been really opened to what you're doing and trying to promote you and trying to push this stuff forward?
Well, I mean, I have my collaborator, which I mentioned, was near Sharif in Jerusalem, and he and his university is open towards these things. As you know, in Israel, they have real problems. So CO2 is not one of them.
Right. I've heard a thing or two.
Yeah. So my hope is that I can go there and do some work as a visiting scientist or something like that.
Yeah.
And continue our work.
Wait till things settle down a little bit first.
Well, I don't think they settle down. No, in Israel, yeah.
Yeah, okay. You're gonna have. I'm telling you, like, wait till it settles down a little bit before you travel over there. And now, what about? It's crazy that in Denmark that you would be getting this kind of pressure put on you, but. Do you have any friends or colleagues in the United States? You said you were getting help from MIT and Princeton.
Yes.
They were protesting this stuff about you firing them.
Yes, I have, for instance, I don't know if you know him, Will Haber.
Will Haber.
Haber.
Sounds familiar.
Yeah.
He has been the advisor to, I think, 2 presidents for science and so on. He's a fantastic scientist.
Is he with a specific university or something? Or
he's at Princeton University of Princeton or whatever it's called.
Interesting.
He's fantastic. And then also, you probably know him, Richard Lindzen.
That also sounds familiar.
Yeah, Richard Lindzen. But they're all, known to be skeptical about CO2 in a rational way. I mean, what they are saying is rational, and they are very well.
How so?
Well, I'm just saying that they have an opinion which is based on rational thought, about science and how science works.
Okay,
So,
I see what you're saying. Now, I want to go back to what the CERN thing. Well, what specifically was the goal with that CERN study that you were a part of in the beginning?
I mean, the whole CERN project was founded because of my work. That was the thing, was to investigate the effect of cosmic rays on the formation of clouds, and that's why it's called CLOUD.
Is it still going there? Are they still doing that?
They're still doing it. I'm not a part of it anymore. That's another story. I was thrown out of the collaboration. I was in the steering group of the whole thing. I was the second person that did this, and I contacted CERN in order to get them to do this kind of experiment.
Yeah, that would seem like a big funding opportunity.
Yes, so the funding has to come outside of CERN.
Oh, okay.
Actually, but they deliver the beam, the particles, and so on,
right.
and some infrastructure. But what happened was that a lot of I think a lot of atmospheric physicists came in to be a part of this cloud project. At that time, just before I was kicked out, what happened? Oh, I forgot. What was it?
Right before you were kicked out of CERN?
Yeah. I was trying to say what I was doing. I just the thought completely disappeared. But I was part of the.
But they adopted. They decided to.
Yes. Okay. A lot of atmospheric scientists went into to the project, became part of the project, and these people were very much, into the CO2 thing because that's how they get funded.
Right.
And what happened was that at that time the movie the Cloud Mystery came out, probably the one you've seen.
Yeah.
And that gave a lot of stir up things. So what happened was that a lot of these people were afraid that if they had me in the collaboration, they might have problems getting funding. So they chose to throw me out, and they said that it was because I had an experiment in Copenhagen at that time. I mean, it doesn't make any sense whatsoever.
So how much progress have they made at CERN?
They showed in 2011, they had the main results showing that ionization is actually helping the formation of new aerosols. It's essentially the same experiment we did in 2007, that is 4 years before they did it. So they can sort of confirm that ions are producing aerosols. But they also had a group, around CERN that tried to put these things into their model, to a big model, atmospheric model, and that showed that these small aerosols would not grow to become cloud condensation nuclei. And now we know that it's because they don't have the right physics in their models. So they're sort of trying to say that this effect is not important for climate. So that's where they are at this moment. And since then...
Really? That's the conclusion they came to?
More or less, yeah. Yes, that it's not particularly important. I think when they came up with the results, even the director of the whole of CERN was saying that they should be very, very careful with what they said and so on, because the politics and so... Everybody was, extremely nervous about saying that maybe the cosmic rays are actually affecting the formation of these particles. So I parted my ways with the CERN project many years ago.
What do you think would change societally, globally, if what you're positing here became just an accepted thing and it wasn't so actively suppressed? If this was something, if we didn't have all these external financial entanglements into climate, and this was just something that was naturally allowed to be out there and be discussed by everybody, what kind of a effect would that have?
No, but I think people would be fascinated with the idea that we are not completely isolated, and stars and star formation has influenced everything here on Earth, and it will still do it in the future. I mean, it's part of life, that all of these things, and it's not just part of life; it has actually shaped life. I think that's an interesting thing.
Totally.
Now, but if we now, I really would like to do this thing with this model to test how it works in the present when we have also greenhouse gases, because ideally it could be that it would say that CO2 is not such a big problem, and maybe we shouldn't be so worried about it. And that could save a lot of money.
Right. Yeah, I mean, my thing is like, the Earth creates these gases and these fossil fuels that we're burning, right? And like, if it's coming from the Earth, it's part of nature. So it's like a part of the fuel that is created by this Earth. It's not like we're extracting some, crazy foreign element from, another galaxy and bringing it here and destroying the Earth. I mean, like, I think everyone would agree across the globe that littering is bad. You don't want to litter, right? You don't want to use the planet as your trash can. But like, we are a fundamental part of the natural balance of this Earth. And we are just naturally evolving. If you want to argue about how fast we're evolving or how good or bad that will be, it's a natural process. And, I think that's become just more apparent now than ever with, all of this talk about AI and stuff like that.
Yeah.
And like super sentience and where that's going to lead.
I mean, we should also say, that CO2, it is a gas of life.
Yeah.
And because we have an elevated, humans' activity has elevated the amount of carbon dioxide in the atmosphere. You've had an enormous greening of the Earth, which is, plants are really happy about it, and especially in where you're on the edge of deserts, and so that's where it's very important that you have more CO2 because you don't have the evaporation of water. Mm-hmm. If you have more CO2, you don't have to have so many stomata. The cells that take up CO2. Mm-hmm. The plant is actually before it makes its leaves, it actually somehow measures how much CO2 is in the atmosphere, and then it gets the number of stomata, these cells.
Okay.
So if you have a period where you had very little CO2, you have many holes in the leaf, but that's also so water will fall out of the leaf. So you.
Oh, wow. What do you got, Siri? What was this?
So I asked if deserts have grown greener since humans have been pumping CO2 in the atmosphere, and the answer is yes, absolutely.
Deserts and drylands have grown significantly greener over the past few decades.
Yeah, it's this enhanced water efficiency in the arid climates are able to narrow the pores in their leaves, stomata. Mm-hmm. So.
Oh wow!
But it's also interesting because if you have fossil leaves. And you can then actually, when you look at the fossil, you can see how many stomata there are. So you can
really?
You can count them. So from that, you can say something about how much
carbon dioxide
there was in the atmosphere.
Wow.
So you can go back, I think, a few hundred million years.
Well, not that long ago, just a few thousand years, I think it's established that like the Sahara was green, right?
Yeah.
And what was the CO2 level like then? Do we know?
I am not sure, but not particularly, but it was higher, yeah.
It must have been higher, right? If the whole Sahara was green and lush.
Yeah, but it's within the last 10,000 years, right? So
yeah, definitely within the last 10,000 years. Oh, as far as we know.
So if you look at the ice cores, where you can look at the small bubbles with CO2, you can go back the last 10,000 years and see what the CO2 level was, and it's more or less constant over that period of time. So it's not probably not.
Is it really?
Changed. Yeah.
Interesting.
And that's interesting also because that's where you have this very beautiful correlation with solar activity. So that cannot be explained by CO2. For CO2 is not changing.
Right. Yeah. That's fascinating. There's been arguments, I don't know if you've ever paid attention to them, but there's archaeologists that debate and argue online like how far back humans were on Earth.
Yeah.
And there's some people that posit that there could have been some crazy ancient advanced version of humans.
I heard about that.
Previously to, 2,000, 3,000 years ago that were using metallurgy.
Okay.
And one of the ways I think they were talking about studying this was taking the bubbles in the ice cores and trying to, there's a way they can measure the isotopes in there to figure out if there was metallurgy on the planet or like metal production or something like this. You ever heard of that?
No, that part I haven't heard, no.
But yeah, and then another way they try to study that is like by studying the continental shelves and seeing like, you know, studying ancient shipwrecks. And
so it's part of archaeology, I guess.
Yeah, there's just a big debate in archaeology about, you know, archaeologists want to kind of like stick to the general consensus story of the history of humanity.
Yeah.
And like when hunter-gatherers came about, when the first actual civilizations came about. And then there was recently that discovery of, not recently, but relatively recently, of Göbekli Tepe in Turkey. It's an ancient site where they believe that there was at least some sort of a civilization there.
Okay.
They weren't just hunter-gatherers because they were creating these huge, they have these, you find an image of Göbekli Tepe, like these big T pillars that are constructed beautifully in these like circles. And it could have been done by hunter-gatherers. So they had to like push back the timeline a little bit, right? And that's Göbekli Tepe, what they've excavated so far. So there's people that argue, and you would call these people, you know, these people are considered alternative historians that want to push back the scientific narrative. And, you know, there's academic archaeologists that argue vehemently against this stuff and saying this is heresy to talk about this.
Okay.
And, you know, it's interesting because, you know, archaeology is another one of those sciences where it's not like a science you can measure in a lab, right? You can't weigh it and measure it specifically. It's like archaeology is very much dependent on the story that we tell of the history of humans.
Yeah.
Right. And then that's, you know, it's kind of like a soft science in that way.
Okay.
But it's just interesting, you know, the reason I'm bringing this up is because I've noticed the same sort of clash between ideologies of different narratives that people want to spin based on human history. And, you know, it's the same thing with climate change. And I'm sure this is, you know, you could extrapolate this into many different sciences, many different areas of reach.
I mean, one of the reasons what I've been very, you know, sure to do is to publish all my results in, you know, very good journals. So you have this peer review and everything, because in that sense you cannot attack me for not doing the right thing.
Well, you know, that's a problem too, because peer review isn't that reliable. Peer review is one of those things that we look at as this holy grail, right? Of being
when you are inside it, you know it's not. But
right, you know, because I've run into people that have you know, been PhDs in certain areas of research and published books that have been peer reviewed. And then like the peer review will be overwhelmingly negative on, you know, on that person's book or that person's research that they've done. And then you go in to read the peer review and you find out the person who did the review on this piece of work, this was not even their expertise. They were in a completely different scientific lane.
Yeah.
Right. So it kind of like throws the whole thing out. You know, it's this whole idea of peer review is like this gatekeeping.
In some sense, it can be, yeah.
And in that sense, it can be bastardized, you know, like anything else.
Especially in climate, it can be a problem. I mean, some papers I've published, it took more than 2 years to get them out. And I mean, through all kinds of problems that you had to overcome.
Yeah. Well, Henrik, thank you for doing this, man. This has been a fascinating talk, and I've learned a ton. Is there anywhere that people can go online to find more of your work or to contact you or anything like that?
They can contact me on my email.
Okay. Do you have a website or anything? Or
I don't have a website, no. I mean, that's just part of university.
All right, what's your? Do you want to publicly give your email? You're probably going to get tons of emails if you give that out publicly.
It's fine.
Okay, go ahead. Tell them your email.
It's hsv at space space.dtu.dk.
Okay. Well, we'll make sure that we link that in the description below for people.
Yes.
So they can actually copy and paste it.
It might work for a few more weeks.
Oh, is that tied to your university?
Yeah, but I will see if I can make a forward to my new email.
Okay, cool. And if you have another email or whatever you want to let us know between now and the time this is published, we can make sure we put that below.
Okay,
too.
that's a good idea.
So,
Yeah, thanks.
Perfect. Yeah, thanks again, man. I really appreciate it.
It's my pleasure.
All right, good night, folks.